Okay, so let me start. Today I may have to leave bit early because I have some other work. So what we discussed last class is this you know this Perez-Horodecky criteria of Simon of Simon. So which was like this this two mode Gaussian state. So this is separate necessary and sufficient condition, right? Necessary and sufficient condition for separability of a two mode Gaussian state. And we said we have seen that this criteria which we have been using so far is this. So if you have this Gaussian state, so gamma having this covariance matrix, so this is covariance matrix which is A C C transpose B, then this condition is basically determinant of A, determinant of B minus, no, not plus, 1 by 4 minus determinant of C whole square minus trace of A j, C j, B j, C transpose j greater than equal to 1 by 4 determinant of A plus determinant of B, where this j is equal to iota sigma y. So, this we have seen that this can be verified by basically using interferometer and in an universal way. So, universal detection of entanglement in any two mode or two mode Gaussian states. Which is based on these criteria. Okay. So, this necessary sufficient condition. So, this we discussed last class. So, what we are going to discuss today is the other criteria by Duan et al. This is again necessary and sufficient condition. For separability of two mode Gaussian state. So, what we are going to discuss is how to detect entanglement in two mode Gaussian state using these criteria. Okay. So, that is what we are going to discuss, and so let me first tell the criteria of this Duan, and then so this is the Duan et al. This is PRL volume 84, page number 2722, 2000. Okay. And this criteria tells you that yes, yes.
Historically, this entanglement test was through EPR correlations, measuring the conditional variances and showing that the product of the variances is less than a quarter.
Yes, yes.
And then we have Simon's criterion, then Diwan Zoller, Mancini,
Yes.
and so quite a few other, Vogel and Schleich, so many
Yes.
people have come up with their own criteria. So, in general, is it possible to just test one criterion in a lab and conclude that a Gaussian state is entangled, or do all these different criteria have different degrees of strength in terms of the test?
Okay, so um, what we discussed last time about this universal detection, which is based on Simon's criteria. So, that works irrespective of whatever the two mode Gaussian state. Okay. It may not be optimal because, but still it works. The scheme that I am going to describe now for this Duan's criteria, it is not universal. Okay. So, it is based upon not universal. I am not saying that it cannot be made universal, maybe, but whatever scheme people have provided is not universal. Okay. This is one thing. So, unless something is universal, you cannot say that it will work for every state.
So, universal as in irrespective of the nature of a Gaussian state?
Yes, it works. Okay. It may not be optimal, that is fine. Now, this EPR criteria, EPR correlation, it works, but again we cannot say that it works as a necessary sufficient condition. If EPR criteria is satisfied, then we say that the state is entangled. Okay. If it is violated, okay, we cannot say anything, right. So, same is the case with see these Duan's criteria, Simon's criteria, it works for arbitrary two mode Gaussian state, no doubt of it, but in the experimental scheme, it might have dependence on the choice of your class of your Gaussian state. Okay. So, say two mode Gaussian state okay, having canonical form of its covariance matrix gamma is equal to this one. So, we have used what A. So, let me call it A1, A2, 0, 0, C1, 0, 0, C2, C1, 0, 0, C2, this is B1, 0, 0, B2. Again, this is a real matrix. Remember, we took this canonical form where A1 is equal to A2 and B1 is equal to B2. This is another canonical form. Okay. So, its covariance matrix where this is of course true that yeah. So, this n1 minus 1 by not n1, this would be a1 minus, maybe let me call it as n1 because to make life easier according to their notation, n1 n2, this is m1 m2, okay, just to make life easier. Okay. So, this is n1 minus 1 divided by m1 minus 1 should be equal to n2 minus 1 divided by m2 minus 1 and mod C1, these are real numbers of course, minus mod C2 is equal to square root of n1 minus 1 m1 minus 1 minus square root of n2 minus 1 m2 minus 1. Okay. So, a two mode Gaussian state having canonical form of its covariance matrix where these conditions are satisfied. Okay. So, this is separable Okay. If and only if and only if you have this criteria that delta, I will tell you what are these, delta u square, which, so this is a 2 mode Gaussian state rho 1 2 with rho plus delta v square rho is greater than or equal to let me see, this is, yes. So, this is a 0 square plus 1 by a 0 square, where where is this a 0? Yes. So, where a 0 square is equal to m 1 minus 1 by n 1 minus 1 is equal to m 2 minus 1 by n 2 minus 1. These are equal because of this relation, and this u operator is equal to a 0 times x 1 minus mod c by c 1 by mod c 1 into 1 by a 0 into x 2, and v is equal to a 0 p 1 minus c 2 by mod c 2 1 by a 0 then p 2. Okay. So, this is lengthy expression. So, it says that a 2 mode Gaussian state having this form of canonical covariance matrix, where of course, these these entries will satisfy this condition, it will have to satisfy this condition in order that this is a valid covariance matrix. This is separable, this state, if and only if you have this kind of. So, this is sometimes these are called EPR operators, okay, U and V. So, if and only if this kind of relation inequality is satisfied.
So, A naught, C1, C2, they are all in a sense scaling parameters to make the terms dimensionless.
Exactly. Yes.
So, can you always bring the covariance matrix to this form?
Yes.
Through what operations?
Yeah. So, I think I discussed in last couple of classes that if you take this gamma, which is A C C transpose B, this is the covariance matrix, by using local symplectic transformation, that means S local, which is S 1 0 0 S 2, where these S 1 and S 2 are elements of S P 2 R, you can always bring this in this form. S local, you can always bring this in this form A, or let us say this is n 0 0 C 1 0 0 C 2, then C 1 0 0 C 2 m 0 0 m, right. This I think we have discussed, right. I mean, by local symplectic transformation you can always do that. Now, to get in that form, what is it that you will have to do? You will have to apply again local symplectic transformation, but this time squeezing. Okay. So, you choose this S 1 for some squeezing parameter, S 2 for another squeezing parameter, and then you can bring it in this form.
Why do we have to make them asymmetric, the diagonal elements?
Asymmetric in the
like n1, n2, m1, m2. Why do we have to do this extra squeezing step? Can't we work with this canonical form?
Yeah. So, that makes life difficult, because you see that if you take n1 is equal to n2, let me see what happens. I mean, this form is a special case of this. Okay.
So if you give me any general symplectic any general covariance matrix, you do some S local and you get to that form always.
Yes.
Right?
Yes.
So after that, so if N1 is equal to N2, the first criteria will be, I think, trivially satisfied, right? Because
N1 is equal to N2. Yeah, this will be satisfied, of course.
and that one becomes that it has to be equal to 0.
Yeah, that mod C1 will, yeah.
Yeah. So mod C1 is equal to mod C2, right?
Yeah. So, but that you cannot always expect, right?
No, but because I can bring any. So these criteria comes from the validity of the.
Yeah. So basically, if I go through the proof of this theorem, you will see that this is needed, not that part. Okay. So here, in general, you need mod C1 and mod C2 to be different for the proof to work. I mean, of course, as I said, this is a special case, so it will work. So I am not going through the proof of that, but in principle, one can. I mean, if you go through the proof, you will see that this is the form which is needed, not that form.
To derive this.
Yes, yes, to derive this. Okay. Because otherwise, you cannot always claim that this is the magnitude is same, right?
Like, yes, sir. Because, yeah, makes sense.
Okay. Right. So this is the basically the necessary sufficient condition for separability of two mode Gaussian state, and I must say that this is much simpler than what Simon has done. I mean, at least the expression wise. Of course, Simon's work provides you much insight, but this is much simpler. Okay. Right. So now what I am going to discuss briefly about an experimental work where this criteria has been used for detection of entanglement in two mode Gaussian state. Okay. So I am actually this paper of Duan I am not going to discuss because I think Cheryl will present it. Okay. This particular paper, yeah. This is what I told her to present because so that is what she is going to do. Okay. Okay, right. So let me erase this part. Yeah.
So that those conditions that you wrote on the right, they are just from the validity of the covariance matrix, right? Or they are something extra?
No, this is actually for a bona fide covariance matrix. This has to be satisfied. Okay.
So this has to be satisfied by any covariance matrix, right? So whenever
not any two mode Gaussian state.
Two mode Gaussians. So now when N1 is equal to N2 and M1 is equal to M2, those has to be still satisfied, right?
Yes, that is true.
Right. So if you take that, then that mod C1 is equal to mod C2 becomes the absolute necessity for a covariance matrix to be valid.
Yes, in this case, yes.
In this case, right? So even if I use that form, if it is a valid covariance matrix, then that has to have C mod C1 equal to mod C2.
No, not like that. The point is that I mean, this is one canonical. See, the covariance matrix of Gaussian state, two mode Gaussian state, has different canonical forms. It's up to you to choose which one is needed. So this is one canonical form. That is also one canonical form, but this is of course a special case of this, right? What I said is that the proof of this theorem, it is valid for this canonical form. If you start with this canonical form, this proof may not work in general. And why is it so? Because you have taken this, in that case this will become 0. Okay. So mod C1 is equal to mod C2. Now for a generic two mode Gaussian state, I cannot claim that mod C1 should be equal to mod C2. Yes, no, even if this N1 and N2 are same, M1 and M2 are same, even then I cannot claim this thing.
So then that condition is something extra than the validity.
Yes, so therefore, I cannot just simply take here N1 is equal to N2 and M1 is equal to M2 and get the condition corresponding to this kind of canonical form.
Okay. But so canonical, because you are using local symplectic transformation, so entanglement won't change under these
Yes,
transformations,
yes,
right?
yes.
So essentially these two states have same entanglement in them.
It has same
It
entanglement.
has, right. But for some reason this criteria won't catch that.
In general, yes, because you know this will impose condition that mod C1 is equal to mod C2, which generally is not true.
So basically this criteria is a universal criteria for a two-mode Gaussian state, but for a particular canonical form you have to first bring it.
Yes, so you will have to bring, see the thing is that because this two mode Gaussian state is known to you, right. So you can always use appropriate canonical symplectic local symplectic transformation to bring it in this form, that you can always do. If you do not know the state, then none of this will work. Okay. So you can bring the state into this canonical form, and that is why I said that you know this proof perhaps will not work for universal detection, because you need information about the state.
While in the other you don't even need anything.
Yes,
You
yes,
just have to take a state,
yes,
do some operation or tomography and get the covariance.
exactly, exactly, exactly.
Here, because you are not doing tomography, you are measuring quadrature.
Because you know the what sort of local symplectic transformation you will have to use on your given two mode Gaussian state, you know that you will have to first decide to bring it in this form. Okay. So, there are some elements of quantum optics which I am not going into details, because you know I think maybe I have requested Bala to talk about at least some elements of quantum optics later. So, here I will assume some of them, and then I will you know later we can have a further discussion, because you know in one course you cannot cover everything, it is impossible, and at that too at a pace which I generally take. Okay. Okay, good. So, this is this paper by Bowen, W.P. Bowen et al. This is in PRL, volume 90, page number 04360111, and then this is 2003. Okay. So, yeah, so this is I think this Timothy Ralph's group from Australia. Okay. Yeah. Right. So, let me first draw the scheme and then we can figure out. Okay. So, this is called OPA, optical parametric amplifier. So, one beam is coming here, another OPA, optical parametric amplifier, they come here, and here a put a phase shift phi, this is a phase shift, and here it is a 50-50 beam splitter, 50-50 beam splitter, right. And then you have the outgoing beams, right. So, it goes this direction.
Excuse me, sir.
Yes, yes.
Can you just give a brief on what is that OPA?
Yeah, so OPA is optical parametric amplifier. So, this is amplifier. So, you know in SPDC, this spontaneous parametric down conversion, what happens, you have a pump beam and then you have a nonlinear crystal, nonlinear crystal, actually you need to have two, but anyway. So, then occasionally you have two outgoing beams. So, if the pump beam has frequency omega p and this is the signal beam omega s and omega I, this is the idler beam, then we have the conservation of energy which is omega p is equal to omega s plus omega I. Also we have conservation of momentum, linear momentum. So, this is the SPDC. Most of the times the beam will pass through, most of the times, but occasionally you have this two outgoing beams. So, this is what is known as spontaneous parametric down conversion. In the case of OPA, what happens is, so this is for OPA, you have this again a nonlinear crystal, right. You have this pump, let us say it is omega p with the frequency, and then you have a signal also. So, this can be single photon, this can be single photon. So, which with this frequency omega s. Then what happens is that now you have two signals each with omega s and also some idler. Okay. So, something similar to that will happen. So, this is again a nonlinear crystal. So, this you can say that this is basically what do we call a of course, you will have this property that yeah, some conservation of energy should be there. Okay. So, like this, I mean this input energy should be equal to the output energy, that should be there. But so, this basically you can see that this will work as a catalysis, kind of catalysis. So, you have the pump beam and you have this extra signal beam, and then in the output you will have this kind of thing. Okay. So, and this is quite useful, for example, in generating, for example, this squeeze lights also. Okay. Yeah. So, here what we are doing is that okay. I am not giving the all the details, but one can figure out that it is not difficult. Okay.
Okay, sir.
Yeah.
Thank you.
Okay. So, now what you do is I will, for the timing I will not draw this thing. So, let me draw this part first. So, you have a again 50-50 beam splitter. So, this is 50-50 beam splitter. Okay. And you have a local oscillator. So, and you have also a phase shift, let me call it as a theta, this is a phase shift. So, this is a local oscillator, you can call it as mode X if you want. So, local oscillator means it is in some coherent state. Okay. So, let us call this alpha x, something like that. Okay. And then you have the detectors here. So, this is basically homodyne. Okay. So, you have these detectors here and detectors here, and then you take this into some coincidence count or whatever, and you measure things. Okay, measure the difference. And similarly, you have here a 50-50 beam splitter, and then you have again a local oscillator. So, I will put a phase shift here. So, local oscillator with let us say alpha y in the coherent state. So, this is I call local oscillator y, and then you have detection, here you have detection, and then you put it through some coincidence, right, and then you take this out. So, it will give you some quadrature, and then you will basically put this through some amplifier which I am calling as G plus minus, and this is your quadrature. So, let me call it as x plus minus x, capital X, and this will give you from here. So, here you have this plus or minus, this is basically some kind of coincidence count or whatever. So, here you give G plus minus and then x. I'll tell you what are these quantities. Okay. So, this is one, you can say that yeah. So, this is one homodyne, and this is another homodyne. This is another homodyne. So, I mean homodyne, we just take the difference of the intensities. So, I will later introduce some noise here, but this is the basically the scheme. Okay. Right, and this theta, same theta here, this theta, this is a phase shift, same theta here, phase shift, here phi is a phase shift. Okay. Right. So, what is it going on here? Okay. Yeah, this is same phase shift, yes, that is what they have taken, same phase shift. Okay. So, what is going on is here through this OPA you create a squeeze state. Okay. So, it may be squeeze vacuum or display squeeze vacuum, whatever. So, squeeze the single mode squeeze state. Similarly, here also, and you take the same thing, I mean like here same single mode squeeze state. Okay. So, like this one and whatever you get here, they are same single mode squeeze state. So, through this OPA you can get that, and now of course, there is a phase shift, but that is not a problem. So, when this so after phase shift this will remain non-classical, this is already non-classical. So, under beam splitter action, the state that you will get, this is an entangled state, 2 mode entangled state. Okay. So, this is 2 mode entangled Gaussian state, because these are individually Gaussian, and by beam splitter action it will remain Gaussian. I mean this is the preparation procedure. I mean I am not saying that this can prepare arbitrary 2 mode Gaussian state, but this is a particular preparation procedure. And then what you do is you have this classical oscillator. So, basically equivalent state, and then you pass through this 50-50 beam splitter. Of course, you will have to use some phase shift, and then you look at the intensity detectors here, and then take the difference of intensity. Similarly here. So, this is what will give you the the position and momentum quadratures. Okay. So, this x, so this x and this y means this is the first mode and this is the second mode. X and y you can think of as modes. Okay. This x and y. So, this x is basically your a x dagger plus a x by root 2. So, this is the position quadrature, and similarly P x is equal to what was the thing, iota a x dagger minus a x by root 2, right, and same is the case with y also. So, you can okay. So, these are the position and momentum quadratures. Okay. So, actually the squeezing are so the squeezing they use these quadrature squeezing. Okay. So, either position, I mean yeah, so what sort of quadrature squeezing they use? Basically phase and amplitude squeezing. Okay. So, but that is okay. So, now so that is at the preparation level. So, now after you do this homodyning, what it will provide you is these information about the position and momentum quadratures, right, in this beam and also in this beam. That is how homodyne detection works. Okay. Right. And then okay. So, here they talked about two criteria. One is this one, this Duan's criteria, and the other one is this EPR correlation criteria by Reed. Okay. So, okay. So, let me first mention that criteria, this Reed's criteria, and then I will tell you about. So, this is the, so this is EPR criteria for entanglement. Okay. Yeah. Yeah. So, local oscillator basically what it does, of course, this will provide you a change in the quadrature, I mean shift in the quadrature. Okay. And through this homodyning you detect that shift in the quadrature. So, if you do the maths, it will come out like this. So, here is your input state, which is some some non classical state, let us say, and here you have this local oscillator, which is a coherent state, and you meet them in the beam splitter. In the output you do the photo detection. Okay. So, intensity measurement, and if you take the difference, that is why I think it should be a minus sign. So, you take the difference, that will provide you the basically the the position quadrature of the state. Okay. And similarly from here. So, this I mean this local oscillator, it is in your hand, and this is the standard way of of detecting the quadrature variables. Okay. Yeah, this is why I said that it will require a bit of quantum optics also. So, maybe later I will discuss about all these things. Okay. Or maybe Vishwanath can also do that. Okay. Yeah. Okay, good.
Excellent, sir.
Yes.
Sir, this phi and theta has any relation that before beam splitter when phase delay you have put?
Yes, yes. So, it
And the theta at receiver.
yes. So, actually you can control these phases to get you will have to have this position and momentum quadrature, right, this x plus and x minus, and that will come by selecting this phi theta properly to get both the position and momentum quadrature. Okay.
So, then this phi will also govern that whether our state is entangled or not. That
No, I mean this will not, see, this phase shift is a classical operation, you can say. It does not change the non-classical behavior. So, by introducing phi, I do not think you can change the entanglement nature of the output state.
Okay.
Excuse me, sir.
Yes.
Actually, by changing phi, you see, for producing two mode squeezed vacuum state,
Yes.
you need to have the squeezing in different quadrant, Q
Yes,
and T quadrant.
yes, yes, yes.
By changing phi, you
Yes.
can change the squeezing direction. You see,
Exactly.
let's say if you make them both squeezed in Q direction or T direction, then the output will not be squeezed. That
Yes,
happens.
yes, yes, yes. No, here actually they are producing it in amplitude and phase squeezing. Okay.
Okay, then I don't know what will be
Yeah.
the nature.
Yes. But of course, no, of course this phi will have a role in that to get the amplitude and phase squeezing. Okay.
Yeah, so non-classicality will not change, but that entanglement. I am talking about the Q and T, quadrature. I don't know how do the results change.
No, I am saying that these introducing this phase will not, it may change the amount of entanglement, but it cannot change the, it cannot make a entangled state to separable state or separable state to entangled.
Actually, it does. If you, let's say, if you are dealing with Q and T quadrature,
Yes.
let's say both of them are squeezed in Q direction, then the output is not entangled at all.
No, you see in this case this is phase and amplitude quadrature. So,
No,
by
that's why I am
by
not,
choosing this
yeah.
phi properly, what you are doing is you know, you can of course change this in amount of entanglement, that is not an issue, okay, by choosing this phi, but this choice of this phi and theta are, I would say it is just to select your class of input states. Like here by choosing phi you select your class of input 2 mode Gaussian state, okay, not just a single one, but you can vary over this parameter,
Yes, yes, yes.
okay.
Okay, thank you.
Okay, yes. So, now let me see that this EPR criteria. So, what should I do? Maybe I will erase this part. Huh? So, this EPR what is that called? EPR criteria. So, this says that yeah. So, so you define this, these are called conditional variances. So, delta square x plus x by y. So, this x and y you understand, this is for the mode x and this is for mode y, okay. So, x by y. Now, what is that? So, this is by definition this is equal to delta square x okay. So, this is actually okay. So, let me write it down first. So, x plus, so plus means the position quadrature, okay. And then it is x minus delta of x plus minus this should be hat, and then this is x delta of x plus minus y, this should be hat, and this is square divided by delta square of x plus minus y, okay. So, now what are these? Let me first write down. So, what is delta of x plus minus? So, x plus you can write it either for x or y. So, this is actually x plus minus its average value, okay. So, this can be either x or y, x or y, x or y, okay. Is that clear? So, this is basically the difference between actual position and momentum observable, okay. So, for plus it is position, minus it is momentum, minus the average value.
This one on the right is Reed's work. This is the result that Reed worked out.
Yes, 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 yes. This is the Reed's work. Yes, okay. Yeah, is that okay? So, this is my definition of conditional variance, okay. So, you calculate the variance of the x mode with respect to position. This is I think, oh no, it is plus minus actually, it is plus minus, yeah, otherwise it does not make sense. So, with respect to the position, and then you take this difference, okay. Yeah, so that is the definition. And
This one is also on delta square x, right? The first term on the right.
yeah, delta square x, this is x square, delta square x, yes. That is why it's a conditional, okay. Yeah. So, Yeah, that is there, and in fact this one can show that this is also same as minimum over, I have used this this parameters g plus minus. Okay. So, this is minimum over this g plus minus, yes, of this quantity delta x plus minus x minus g of plus minus delta x plus minus y and then square and then average. Okay. Yeah, so this is somehow, that is why they have, this is a kind of amplification. So, whatever data you get, you amplify it by this one. Yes.
This criteria is for this particular setup or
No, 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 no.
because G is
Yeah, that is, well, in this setup they have introduced this G in this way, but you can forget about the second part. This is general definition for this conditional variance. Okay. Right. So,
this is a this criteria is
I have not yet written the criteria, this is just definition for the
Oh.
conditional variance. So, this EPR criteria, this is also called sufficient condition for inseparability. So, that means, so it says that delta square x plus x given y into delta square x minus x given y, this is less than 1. So, if this condition is satisfied, then we can say that this is of course for 2 mode state, 2 mode state is entangled. Okay. And this is by, let me see, yeah. So, this was done by M.D. Reid and Peter Drummond. Okay. PRL volume 60, page number 2731, then 1988. Okay. So, this is the condition, sufficient condition for inseparability. Okay. Good. But of course, if if a state is entangled, we cannot say that this condition will be satisfied. Okay. So, this is a sufficient condition. Okay, good. So, now one can also introduce losses to check the robustness of this criteria, like maybe for initially 2 mode Gaussian entangled state, this condition will be satisfied, but if I introduce some kind of noise locally, it may get violated. Okay. Right. So, that is a possibility. Okay, good. So, I will come back to this noisy part later, and one can also cast this inseparability criteria. So, this is let me draw here. So, this is for read. Inseparability criteria, do you remember what is it that we have done? Duan's criteria, what was that? Right, that condition. Okay. So, that is the condition. So, what one can do is the following, that um, um, yes. So, again this is what was the condition in terms of necessary sufficient condition for inseparability, right? Yes. So, that was, what was that, greater than equal to a square, a 0 square plus 1 by a 0 square, something like that, right?
They are separable if it is
Greater than equal to something, right? Yes. So, sufficient condition for inseparability of two mode Gaussian states. This is again Duan's criteria. Okay, Duan et al.'s criteria. So, this one can prove that this is nothing but square root of delta square, again I will tell you what it is, x plus minus y. So, this is a kind of superposing the modes, delta square x minus x plus minus y, this is less than 1. Okay. So, this is the necessary and sufficient condition, and yes. So, this should be necessary and sufficient condition. Yes, yes. So, yeah, it should be necessary and sufficient, it should be necessary and sufficient. Okay. Right. Okay. Now, this is, what is this? This is the, yeah, it's too many symbols, but let us, okay. So, this delta square of x x then x plus minus y. Okay. So, this variance, this is equal to yeah. So, this is a kind of tricky definition. So, this says that this quantity is the minimum of the variance of the sum or difference of the operator x between beam x and y normalized to the two beams. So, normalized to the two beam short noise. Okay. So, let me see how to put it in that way. So, this is, it says that this is the minimum, okay, of the variance, minimum of the variance of the sum or difference of the operator between beams. So, sum which is x x plus x y, okay, or difference which is x x minus x y. Okay. Now, what is x x and x y? Yeah. So, this I have defined, right. Yes, sum or difference. Yes. So, this should be actually sum or difference of the operator x between the beams. Yeah, so this should be actually yeah. So here it is, of course, this is bit tricky. So here I will put x plus minus. Okay. So in that case, it will be x plus or plus minus, here also x plus minus. Okay. Right. So either in the position quadrature, sum or difference, or momentum quadrature sum or difference. Okay. The sum or difference of the variance is the minimum of the variance of the sum or difference. Okay. Variance of either this or this. Okay. Normalized to the two beam short noise. Yes. So otherwise it does not make sense. Normalized to the two beams short noise. Okay. Two beam short noise. So in fact the expression they have written is the following one. So this expression, this is equal to minimum of this average value delta x, this is x, and then so again it should be plus minus, and here it is plus minus delta x y, again plus minus square. Okay. So yeah, so this minimum is so this minimum is over these two. Okay. Either you take sum or difference. Yeah. Yes.
In all these criteria,
Yes.
so we always take the sum of operators in one quadrature and the difference in the complementary quadrature.
Yes. So why we take
Why-
so?
why
Yes.
this
So
common-
because you see that here itself, yeah. So you see that if I take this thing x1 plus x2 for the two mode case and p1 minus p2, right, they will always commute, right, and we know that these EPR state, which is basically two mode squeeze vacuum state, okay, with the squeezing is equal to infinity, plus infinity. If I take that, this is my EPR state. For that state, I mean that state is actually a common eigenvector of these two, right, and we know that this is a maximally entangled state, although unphysical, this is a maximally entangled state. So therefore their correlation is maximum, you can say that, okay, whatever way you want to see. So what, because this is unphysical, it is not good to talk about such a EPR state. So what one can think about is some modification of these operators and thereby modifications of the corresponding common eigenstate, okay, so that it can capture other correlations also. And if you look at these variables that we introduced, these u and v, right, those are something like this, something like some factor times x1 and then plus some factor times p1 or x2, yeah, something like this, and v is equal to some factor times x2 minus some factor times p2, something like this. Okay. This is how we introduce u and v.
Earlier you both had minuses when you wrote the project.
That is okay, that is fine, plus or minus, you can, that is why you have to introduce, I think they introduce their C1 by mod C1 and then C2 by mod C2, so it depends upon that, their signature, that is okay. that is up to our hand. This is P 2. Oh no, sorry, this is P 1, yeah, P 1 P 2, okay, something similar to that. Okay. So, this is, you can say that this is, so this is a more general case than this one, this is a more general case than this one.
They are computing, so they capture every information.
Not every, at some state they will capture.
Why not every? Because so these are not complete set.
Yes.
So the sum and difference is because they have common eigenstates. Then you know those those common eigenstates, and the variances are measured over those common eigenstates, and then you study the correlations, so on and so forth.
Exactly.
So, like, what kind of what kind of information is left there after measuring the common eigenstate of these two objects?
No, you see, if there is a common eigenstate, which I think it should be, so then you know that similar to this EPR state, these common eigenstate will have quantum correlation, which may not be maximum one, but some quantum correlation is there. Okay. So, if you measure those quantum correlation, it should be reflected.
Yeah, because these are all Gaussian states, right? So every information is in the covariance matrix.
Yes.
And covariance matrix is essentially various expectation values of the product of x2.
Right.
So once I have x1 plus x2 and p1 minus p2, that's why I have their eigenvalues, I have measured them. Right? So in principle, if I have measured them, I can measure every product and its expectation.
Yes, in principle, yes.
So hence, I have all the information there is about the Gaussian state once I measure these two.
No, not all the information, you know, you do not get all full set of information. See, even if you can, even although I said that these are not very realistic observable, but let us say even if you perform joint measurement of this, it will not provide you the full details of the state. Okay. So, and we are not also interested in that. What we are interested in, what sort of correlation is there, right. So, if you look at the Duan's criteria, they look at this kind of correlation, delta u square plus delta v square greater than equal to something, I think a0 square plus 1 by a0 square. But you know that is the sum of uncertainties and product of uncertainties, they are related. So, you can always cast that. So, the EPR criteria by Reed, it is in terms of product of uncertainties. Okay. Yes. So, yeah. So, basically what they have done here is that after production of this kind of entangled state, they you know, through this homodyne measurement, they calculated these quantities, like in this case of conditional uncertainties, and in the case of Duan's criteria, this kind of uncertainties, whatever I mentioned, yes, this kind of uncertainties. And then they checked, of course, if these are satisfied, then you know that your two mode Gaussian state is entangled according to both the criteria, right. Now, what they have done? They have introduced now some noise, okay, to check the robustness of this scheme. So, basically they use some photon loss noise. Okay. So, what you do is yes. So, here you have a phase plate, halfway plate. So, you are looking at the polarization of the photon, okay, and then you send it through a PBS. This is polarizing beam splitter. Okay. So, in one arm you know detect basically is so there will be some loss. Okay. So, yeah. So, this corresponds to loss. Okay. You do not take care of what is there, and then the other one goes here. So, for example, by this halfway plate, what you are doing is you are preparing a particular polarization particular polarization basis, and then like polarizing beam splitter, only the horizontally polarized beam will pass and vertically one will go through, or vice versa. Similarly here. So, this is so loss x I say, because this is in the x beam, and similarly here you put a half a plate and then a polarizing beam splitter. So, it will come and then again it will go. Okay. So, this is a PBS. So, this is loss y. So, this is photon loss, okay, because you are not looking at that. Rest of the things are same.
So this polarization does not interfere with the whole homodynamic detection process.
No. Yeah. Okay. So, using this photon loss, you can now see what will be the modifications of both these criteria, EPR criteria and these Duan's criteria. Okay. So, yes.
So this loss signal which we are getting from both PBS,
Yes.
so those both also will be entangled.
Yeah, this will be entangled, of course, otherwise it does not make sense. Yes.
No, the loss signal which is going, loss path.
Loss
Two
part.
paths for loss.
These two.
Also will be entangled.
Yeah, it can be in principle. Yes.
So if this setup is used for some communication, so that can be one eavesdropping path.
Perhaps. Yes. Of course. Yes. Yeah.
Okay, sir.
Okay. So now what you can do is one can figure out what will be the modification. Yes. So now what they have taken is well, this you can also take care of let us say these detectors are not perfect, they have also some inefficiency in the detection. Okay. These are inefficient detector, like here also there are some inefficient detector. So, ultimately everything can be cast in this form. Let me erase this part. Yeah, unfortunately I am not going through all the details, but one should look at this paper and sit down and do all the calculation. In principle one can do, it is not difficult, but one will have to do that. Okay. So, basically if you use eta as the detection efficiency, so that means eta is equal to 1 means 100% efficient. Okay. Then this criteria, okay. So, what will happen here is that this delta square x, so the EPR criteria times delta square x minus x given y, this will turn out to be, with this detection efficiency and all that, it will turn out to be 4 times 1 minus eta plus twice eta minus 1 divided by eta into delta square x, this is squeezing, okay, plus delta square x, this is inverse, I mean the inverse of this is qz, and minus 2 then plus 2. Okay. So, maybe I should not write like this, let me write it in a different way. So, this is 4 times 1 minus eta plus twice eta minus 1 divided by eta delta square x, this is squeezing. So, this is a uncertainty in the squeezing. So, which we have taken basically the squeezed light. So, this is uncertain inverse of that, minus 2 plus 2 and then this is square. Okay. So, what is this uncertainty in squeezing? Because we said that the initial states are, you are looking at the quadrature squeezing in this case, amplitude and phase squeezing. Okay. Now, whenever you do this amplitude phase squeezing, this is also for other quadrature squeezing also, you will have some sort of uncertainty in the squeezing. So, this is so I am not writing the exact form of this, one can in principle figure out what is this form, the exact form of this. So, in fact, they have experimentally also figured out what will be the values of this squeezing. Anyway, so let me tell you the ultimate thing is that
Property of the prepared state, right?
prepared state, yes. So, there is some uncertainty in the squeezing. So, what it tells you, so this is not the EPR criteria, this is the left hand side part of EPR criteria. So, if you take eta is equal to half, so detection efficiency is 50%, then this will tell you that this delta square x plus x given y times delta square x minus x given y, this will turn out to be 1, and this is independent of the level of squeezing. I mean, how much you are squeezing, it is independent of that, which is independent of this delta square x squeezing. Okay. Now, this being 1, it means what? It means that it is not satisfying the EPR criteria. Now, if it does not satisfy EPR criteria, what can you say about entanglement? If it satisfies EPR criteria, then this is inseparable, that means entangled, right?
But it is sufficient. Yeah.
It is sufficient, but if it does not satisfy, we can't say anything. So, initially actually one can check that when this eta, so maybe they have also done it. So, what happens if eta is equal to 1? So, eta is equal to 1. So, delta square x plus x given y, delta square x this is minus x given y, this will be this is 0, this is 1, the 4 is outside. So, 4 by delta square x squeezing plus delta square x squeezing inverse, right. Now, what can I say about this value? Is it can I say that this is less than 1?
That would depend on what is just the variance system or
Yeah. So, what is the condition? This has to be less than 1, right?
Yeah, so greater than 4.
Yes. So, delta square x squeezing plus delta square x squeezing inverse has to be greater than 4, right? Yeah. Now, yes. Now, usually how much squeezing one can have? This is not much. I think it what?
25 decibel is
Yeah.
the highest that people have achieved.
Yes,
now,
yes.
now so far. That corresponds to R less than 2, little less than.
Less than 2.
This is very, but 2003 paper.
Yeah, so maybe 25 decibel was achieved around 2010. I don't remember the year, but
Actually, it is 15 decibel. 15 decibel in 2016.
15 decibel.
15 decibel, yeah. No, I think this condition will be satisfied. Okay, this will be satisfied. Yeah. for eta is equal to 1, otherwise nothing can be detected. Okay. So, this will be satisfied, I do not know exactly what is the exact values of this, I am sure it will be satisfied. Okay.
Eta is the detector.
Eta is the detection efficiency.
What
Yes.
about that? The loss in the arm.
Yeah. So, everything you can you can cast it in terms of detection efficiency, right? Because you see a 100% efficient detector means everything will pass through the detector, right? And if it is not 100%, what you can do, you can put a beam splitter with some transmittivity and reflectivity. So, let us say this is your transmittivity. Okay. So, this amount will go through and then reflected beam will come through. Okay. So,
This leads to loss in intensity, right?
sorry?
This operation, this leads to loss in intensity. At the
Loss intensity, yes.
And because the operations, so after that loss, they are all linear operations, so loss in intensity won't affect the outcomes. Hence, FP can be casted in the loss in the detection itself.
No. You see these loss. See, the thing is that if you have the loss in this detection, you will have to modify the detection process, right? Okay. So, that modification they have done, the basically this is the modified version. Yeah, of course, everything here is linear, that is true. Okay. So, yeah, for eta is equal to 1, of course, this has to be satisfied. However small you can think of, because this is inverse, this will be very high. Okay. Right. But what you can show is that for eta less than half, okay. So, for eta less than half, I think this quantity, this delta square x plus x given y times delta square x minus x given y, I think this will be greater than or equal to 1. Okay, for eta less than half, and therefore, this EPI criteria is not satisfied.
Always.
Yes, that is what they are claiming. I guess one can also prove that.
Even that, so that quantity is a function of, so that will, so if eta goes away because you are putting it to be less than half,
Yes.
then the only variable left is the squeezing.
Yes.
But that is in our hand, that as the time goes on, we can make it.
Yeah, I think one can, whatever be the squeezing, non-zero squeezing you can think of, this entire thing when eta is less than half will be always greater than equal to 1. Okay. So, therefore, if your detection efficiency is less than 50%, then this criteria cannot capture entanglement. Okay, good. Right. Okay. So, let me write down. So, this was for the EPR criteria when you have loss. Now, let me write down the modified version of these Duan's criteria when you have loss. So, when you have loss, then this, so Duan's criteria under loss, under photon loss, actually this is photon loss. So, what it will happen is that this is, so this I mean this expression, you remember this was our expression, delta x plus minus y time delta square x minus x plus minus y. So, this was less than 1, right, for the for the criteria necessary sufficient criteria for entanglement of two mode Gaussian state. So, when you have loss, that means let us say with efficiency eta, detection efficiency, this is eta times delta square the squeezing, uncertainty squeezing plus 1 minus eta. Okay. So, this is how you get. Okay. And as a result,
So this result is also mentioned in that paper.
yes, in this paper, yeah. So, what happens if I take eta going to 0? So, that means very bad detector. So, this approach is 1, right. So, eta going to 0, this approach is 1, but is it less, how is it behaving? I mean, assuming this is small enough. So, then this must be, actually this is less than 1 or what? I mean, if I put eta is equal to 0, then this is 1, right. But if eta is not equal to 0, so this is actually less than 1 for eta greater than 0. Is that a correct statement? Because this is small, generally this is uncertainty very small. So, therefore, this is, I can say that this is less than eta. So, this is less than eta and this is 1 minus eta. So, therefore, it has to be less than 1, right. Okay. So, you see that for positive eta, whatever be the value of eta, this is less than 1, and this means that your two mode Gaussian state is entangled, right. So, it does not matter what is your detection efficiency of the detectors in this particular lossy model, the Duan's criteria always detects entanglement in two mode Gaussian state. Is that clear? Right. But this Reed's criteria, EPR criteria does not detect entanglement below 50% efficiency. So, you can say that in this respect of detecting entanglement in two mode Gaussian state which are produced in this way through the squeezing, Duan's criteria works much better than this EPR criteria. Now, one might say that look, you have taken particular kind of entanglement, you have taken particular kind of noise model. So, how can you compare EPR criteria with this Duan's criteria? That is of course true, and there is no universal there is no unified platform where you can compare, right. So, yeah, so this is basically the issue, and in fact this Duan's criteria works for this kind of two mode Gaussian state. I do not know if you change the nature of the Gaussian state whether this will still work.
So the states produced by this procedure, they have that conundrum.
Yes. Yeah. Well, even if it is you do not have canonical form, you can cast it in that canonical.
Yeah, but then there is no operation here which is doing.
Yeah, right. But in principle, you can do that. What is it? These are squeeze states, right? Two more squeeze vacuum state, let's say, and then through the beam splitter, you don't actually you will have those kind of covariance matrices only.
But then, so if I take any say general state, but I don't know it, hence
Then you cannot use this.
Then we cannot. So first I have to know the state.
Yes. So I am sure that the kind of two mode Gaussian state produced here, it can be cast in that form. It will always have the covariance matrix in that form.
It will automatically have.
Yes. It will always happen.
because you are taking two single mode squeeze state and then interfering them.
Yes.
So,
I mean, one can in principle check that, but this should be. Okay. So, yeah, so some of the things, I mean, I think the optics part I have not touched much. So, for example, this how this OPA acts to create the squeeze state, how the the phase shifter acts, how this lossy this PBS works. This is simple, this is not difficult. And then what happens to this homodyning, and then how this inefficient detection will appear in this expression. So, this none of this we have discussed. In principle, one can sit down and calculate all these things. It's not difficult, one can do that. Okay. Yeah, so why I wanted to talk about this work is that first of all, it is an experimental realization of Duan's criteria. Secondly, it provides you a kind of comparison between the EPR criteria and Duan's criteria. Okay. And in lab, this homodyning is very easy, it's not difficult, one can always do that. Yeah, but again this is not universal, and I am not sure how will you modify it to make it universal. Okay, so I will stop here.